Okay, let's dive right into this explainer. Today, we're unpacking something absolutely foundational to artificial intelligence. We are stepping directly into the mind of an AI to really understand the nuts and bolts of deduction. We're going to look at how an agent, armed with literally nothing but basic logic, can navigate dangerous, hidden environments and actually make smart, calculated decisions. To kick things off, I want you to think about this for a second. How does a machine actually know something it can't directly see? Right? When an AI doesn't have the whole picture, what computer scientists call a partially observable environment, how exactly does it figure out what's waiting around the corner? This is the incredibly high-stakes problem of teaching an AI to reason. It's not just about reacting on the fly, it's about deducing hidden information so it can survive. So, here is our roadmap for today. First, we'll meet the logical agent. Then, we'll talk about surviving the Wumpus World. Next, we'll break down the mechanics of propositional logic. And finally, we'll wrap up with the power of theorem proving. Okay, let's jump into part 1, meet the logical agent. Our main protagonist here is specifically known as a knowledge-based agent. Now, unlike a simple reflexive program that just reacts to a stimulus by pure dumb luck, this agent has a memory and it actually has the ability to reason. It operates on a wonderfully strict, divided architecture. Down at the foundation, you've got the knowledge base. Think of this as the agent's memory. It stores all the domain-specific facts and the rules about the world it's living in. And then sitting right above that, you have the inference engine. This is the brain of the whole operation. It uses domain-independent algorithms to crunch the facts stored in the memory and figure out its next move. Whenever the agent learns something new, it tells the knowledge base. And when it has to make a choice, it asks the knowledge base. It's just a perfectly elegant two-part system. Moving right along to part 2, surviving the Wumpus World. Picture a literal life-or-death scenario mapped out on a tiny 4x4 grid. This is the infamous Wumpus World. Somewhere hidden in this pitch-black cave is a glittering bar of gold. But there are also bottomless pits. And even worse, there's the Wumpus, this hidden, hungry monster that will absolutely eat our agent if it steps into the wrong square. Our agent drops into the bottom left corner, completely blind what's waiting in the rest of the grid. Now, before our agent even takes a single step, let's look at the strict limitations it's working under using the PEAS model. Performance, environment, sensors, and actuators. The performance stakes here are huge. Grabbing that gold scores you a cool, positive 1,000 points. But falling in a pit or getting eaten, that's negative 1,000 points. Which, let's be honest, for an AI is a really bad day at the office. To survive, the agent has to rely purely on its sensors. Any square sitting right next to the monster is going to be smelly. Squares next to a pit are breezy. If it happens to be standing on the gold, it'll see a glitter. As for its actions, it can turn, move forward, shoot its one single arrow, or grab the gold. Let's do a quick play-by-play of the agent in action. The agent starts out at square 1-1 and perceives absolutely nothing, so it's safe. It decides to take a step to the right, into square 2-1. But suddenly, its sensors go off. It feels a breeze. According to the hard-coded rules in its knowledge base, a breeze means there's a deadly pit in an adjacent square. But the tricky part? It doesn't know which one. It could be directly above in square 2-2 or further right in 3-1. Since it doesn't know for sure, it wisely backs up to the starting square. Okay, having retreated, it tries a different route, moving up to square 1-2. This time, there's no breeze, but it smells a terrible stench. Now, it knows a stench means the Wumpus is adjacent, so it's either up at 1-3 or to the right at 2-2. But watch how the AI brilliantly deduces exactly where this monster is. It remembers that the Wumpus cannot be at 2-2 because if it was, the agent would have smelled that same stench when it was previously standing at 2-1. Therefore, the Wumpus absolutely has to be at 1-3. The agent literally just deduced hidden knowledge using pure, undeniable logic. Which brings us nicely to part 3, mechanics of propositional logic. That deductive leap we just watched, it's incredible, right? But how does the machine actually calculate that? Well, we have to define the single most important concept in all of logical reasoning, entailment. Entailment just means an unavoidable logical consequence. If fact A and fact B are true, fact C absolutely undoubtedly has to be true. It's not a guess, it's a mathematical guarantee. When our agent figured out the Wumpus was in square 1-3, that specific location was mathematically entailed by the facts the agent already had in its memory. To actually calculate this stuff, the agent relies heavily on truth tables and logical connectives. It takes simple facts, like assigning a P for a pit and a B for a breeze, and it binds them together using basic logical operators. Things like and, or, not, and implies. So it might write out a rule saying, a breeze in 1-1 implies there is a pit in 1-2 or a pit in 2-1. These truth tables act as the agent's mathematical weapons, defining exactly when these complex sentences are true or false based on the environmental clues. Now, one way the agent can figure out what's true is through a brute force method known as model checking. It literally just builds a massive truth table enumerating every single possible reality or model just to see if the formula holds up. But look at the math on this for a second. For just 5 variables, you're looking at 32 rows. For this tiny little 4x4 Wumpus cave, a full truth table requires 128 rows. As the world gets even slightly bigger, this exponential growth makes brute force enumeration incredibly slow. It's just entirely impractical for a modern AI. And that leads us to our final section, Part 4, the power of theorem proving. So, how do we fix this massive computational bottleneck? Easy. We ditch the sluggish, brute force approach of model checking, where we list out all possible worlds, and we pivot to theorem proving. With this method, the AI applies sound inference rules directly to the sentences already sitting in its knowledge base to construct a logical proof. It's sleek, it's rule-based, and it's highly efficient simply because it gets to completely ignore all the irrelevant propositions. A core weapon in the AI's theorem-proving arsenal is the classic modus ponens rule. It's super straightforward. It just says if you know that alpha implies beta, and you also know for a fact that alpha is true, well, then you can immediately conclude that beta is true. By stringing together these incredibly simple, sound inference rules, the agent can build a chain of conclusions leading right to its goal. It's generating brand new sentences from old ones without having to check every single alternate reality. Another seriously powerful tool here is proof by contradiction. The agent basically proves a sentence is true by assuming the exact opposite is true, and then proving that that assumption creates a total logical impossibility. So in our Wumpus world, to prove a path is safe, the agent assumes, okay, let's pretend there is a pit here. If that assumption directly contradicts the breezes it has already felt, boom, the path is proven safe. It brilliantly shows that the alternative is just logically unsatisfiable. To actually automate this whole process, computer scientists use a really elegant 3-step code cracker called the resolution algorithm. Step 1. The AI converts its entire knowledge base along with its negated goal into a standardized format called conjunctive normal form, or CNF. Step 2. It applies the resolution rule to pairs of clauses that contain complementary literals. You can kind of think of this like matter and antimatter. One has a positive trait, the other has the exact same trait but negative, and when they touch, they cancel each other out. Then, step 3. It just keeps resolving these pairs until it produces an empty clause. Finding that empty clause proves the contradiction, which in turn mathematically proves the original goal. And believe it or not, we can optimize this even further. If we restrict the AI's language to specific formats, like horn clauses, it gets a massive speed boost. Horn clauses are simply sentences that have at most one positive literal. Formatting the agent's knowledge this way allows the AI to use really snappy forward and backward chaining algorithms. And this is the real game changer. It allows the AI to decide entailment in linear time. Linear time means that even if the cave gets 10 times bigger, the agent's thinking process only takes 10 times as long, not 1,000,000 times as long like the old brute force method. It scales beautifully. Our agent can basically think on its feet almost instantly. We've seen exactly how an agent uses its inference engine, along with propositional logic and theorem proving, to deduce the location of a hidden monster in a dark cave. But I want to leave you with one final thought to really reflect on. How does this simple Boolean logic, just basic ones and zeros, true and false, how does that actually scale up to power the incredibly complex deduction-making AI systems that are fundamentally changing our world right now? Because the rules we cover today, they are the absolute bedrock of machine reasoning. Understanding this little Wumpus world is literally your first step to understanding the minds of modern AI. Thank you so much for joining me on this explainer, and keep learning.